So, we're surrounded by electric motors, right? They're the real workhorses of our modern world. But have you ever wondered what happens between the power outlet and, say, a massive industrial machine? I mean, you can't just plug it in. That would be a complete disaster. Today, we're going to dive into the brilliant technology that tames all that raw power, the electric motor drive. Okay, let's get into it. First, we'll start with a big question. Why do we even need these drives in the first place? Then, we'll jump back in time and look at the classic DC motor drive, the original champ for precision control. After that, we'll explore why the whole industry shifted over to AC motors, and we'll unpack the clever electronics needed to tame them. And finally, we'll pull it all together and put these two amazing technologies head to head.
All right, first things first. Why do we even need to control motor drives? You might think it's simple. Just give the motor some juice. But trust me, it's a whole lot more than just a simple on-off switch.
I mean, it's a totally fair question, right? But for a big industrial motor, just slamming it with full power from the get-go is, well, it's violent. You get this massive inrush of current. We're talking 6 to 8 times the normal amount that can cause voltage to dip across the entire power grid. At the same time, you get this huge instant jolt of torque that sends a physical shockwave through the whole system. You can imagine the damage that does to gears, belts, and the motor itself over time. Engineers have a name for these high-stress moments, transient operations. This isn't when the motor's just cruising along. It's every single moment of change. Starting up, slowing down, slamming on the brakes, or changing direction. A motor drive is like an intelligent middleman. It carefully manages the flow of power to smoothly handle all these transients, protecting everything, both the electrical grid and the expensive machinery, from those destructive forces. So, how did we first solve this problem? For that, we've got to look at the original champion of variable speed, the DC motor. For decades, if you needed precise, adjustable control over something, this was the undisputed king of the hill. You know, the absolute beauty of the DC motor was its simplicity. The physics behind it are just so direct. The parts of the motor that create the twisting force or torque and the parts that set the speed are controlled by separate electrical inputs. So you've got the armature circuit for torque and the field circuit for the magnetic field. Since they're separate, you get this wonderfully simple direct control. That's why they were perfect for precision tasks way before we had all the complex electronics we have today.
And they were controlled in two main ways, both centered around the motor's base speed. Think of that as its normal, most efficient cruising speed. For anything below that speed, you use armature voltage control. You're basically just turning a dial on the voltage going to the armature. This gives you direct, stable speed control, while keeping the torque maxed out, perfect for heavy loads. But for speeds above that base speed, you switch over to field flux control. Here, you start to weaken the motor's internal magnetic field. This lets the motor spin much faster with the same voltage, but you trade off some torque for that extra speed, which gives you constant power.
Now, this graph is awesome because it shows you exactly what we're talking about. You can see those two distinct zones. On the left, that flat line is the constant torque region. As the speed climbs from 0 up to that base speed, the torque just stays rock solid at its maximum. That's your armature voltage control at work. Then, boom, right at the base speed, the curve changes. As you push the speed higher, the torque starts to fall off. That's the field weakening kicking in, and you can see how it creates that constant power range. It's just a really brilliant two-stage approach to control. Of course, getting it to stop is just as important as getting it to go. Plugging is the brute force method. You literally reverse the power to create a huge braking force. It's fast, but man, is it inefficient. Dynamic braking is a bit smarter. You disconnect the motor and dump its energy into a big resistor, basically turning all that motion into heat. But the most elegant method by far is regenerative braking. Here, the motor acts like a generator, turning its own momentum back into electricity and feeding it right back to the power supply. Super efficient. Now, DC motors gave us amazing control, but the motors themselves had one big weakness, a real Achilles heel. And that mechanical problem is what opened the door for a tougher, more reliable successor. Which brings us to our next section, the rise of AC drives. So here's the deal breaker. DC motors have brushes and commutators. These are physical parts that rub together to get power to the spinning part of the motor. They wear down, they create sparks and dust, and they need constant, expensive maintenance. The AC induction motor, it has none of that. No brushes, no commutator, no internal contacts at all. It's just mechanically simpler, way more rugged, lighter, and cheaper. The motor itself is just a better physical design, hands down. This quote really just says it all, doesn't it? For any simple on-off job, the AC induction motor has been the go-to champion for more than 100 years. The challenge was never about the motor itself, it was always about controlling it. How could you give this simple, tough-as-nails workhorse the same fancy variable speed control that DC motors had from the start?
And that question brings us right into the modern era of motor control. How do you tame that workhorse? Well, this section is all about the electronic wizardry that finally unlocked the true, full potential of the AC induction motor.
So, an AC motor's speed is basically set by a formula involving the power's frequency and the number of poles inside the motor. Early on, people got creative. Pole-changing motors had special windings that let you switch between 2 or 4 different speeds. Kinda clunky. Stator voltage control just starves the motor of voltage to slow it down. It's not very efficient, but it works for simple things like fans. But the real game changer, the true revolution, was variable frequency control, or VFC. The idea is simple. If you can precisely control the frequency of the power you feed the motor, you can precisely control its speed across the entire range. So how does that even work? A modern AC drive does this little three-step dance with electricity. First, it takes the AC power from the wall, and a rectifier turns it into DC. This nice, stable DC power gets stored for a split second in some capacitors. And then comes the magic. An inverter, using super fast switches, chops up that DC power and rebuilds it into a brand new, perfect AC waveform. This inverter stage is what gives the drive its incredible power and flexibility to create any frequency it needs.
Now, I know this slide shows a DC drive, but it's a perfect way to visualize the principle behind a modern AC inverter. See how the voltage is switched on and off in these really sharp pulses? By changing how wide those pulses are, a technique called pulse width modulation, or PWM, the drive can create an average voltage that looks and acts just like a perfect sine wave at any frequency it wants. It's like electronic magic, letting a drive create the perfect power source to make an AC motor do exactly what you want it to do.
Okay, we've covered a ton of ground here, right? From the simple physics of DC control all the way to the seriously complex electronics of modern AC drives. So let's zoom out and look at the big picture. This table really is the ultimate cheat sheet. DC drives, they give you beautifully simple direct control over torque, but the motors themselves are a pain. They're expensive and need a lot of maintenance. AC drives, on the other hand, need all those fancy electronics to work, but they let you use cheap, absolutely bulletproof induction motors that need almost zero upkeep. For years, DC held on in jobs that needed tons of torque at low speeds, like in steel mills or on giant cranes. But as AC drive tech gets better and cheaper, it's starting to take over even those jobs too. And that really leaves us with one final big question. Now that modern electronics can make an AC drive perform better than a DC drive in almost every way, and with the cost of that tech just plummeting, are we watching the end of the line for the technology that started this whole thing? Or will the pure, simple physics of the DC motor always guarantee it a spot in our industrial world? It's something to think about. Thanks for tuning into this explainer.
Thanks for watching. Please visit the channel for more content and don't forget to subscribe and like if it was helpful. Comment if something is wrong.